Dear student, this is the third video regarding with the aliphatic nucleophilic substitution reaction. In first video, I explained about the nucleophile and nucleophilicity. In the second video, I explained about the SN1 reaction, and in SN1 reaction that some few points we discussed, that is general reaction, kinetics of the reaction, mechanism of the reaction, 3D animated SN1 reaction, and the structure of carbonate. These 5 points we covered in the previous, the second video. That is, now in this is the third video regarding the same chapter. Now in this video, the next point that we have to discuss, the energy profile diagram, the stability of the carbocation, stereochemistry of SN1 reaction, ion pair mechanism in SN1 reaction, and effect of solvent in SN1 reaction. So these 5 points now I am going to discuss with you. So let us start for the first point of the third video, the energy profile diagram. Now in this energy profile diagram, you can see there are one maxima in the energy profile diagram, one minima is there, and again one more maxima is there. And here there is a reactant, and here there is a product. The energy gap between these two is denoted by delta E, that is the reactant and the product. The energy gap between these two is denoted by delta E. On the x-axis, the reaction coordinate, that means how the reaction proceeds, and on the y-axis, the free energy, that is the energy gap between the maxima. So look at the first maxima, which is, that is the delta E1 star. So this is the maxima where you have a largest that is that this is a highly energetic structure. Then the next carbocation, when the energetic structure of first maxima get collapsed into the carbocation, then energy of carbocation get decreased and you'll get the minima over here. And after that, in the second step, as the nucleophile approaches to the carbocation, so again, second maxima we will observe over here. And after this, the that the carbocation collapse into the product. So this is the energy profile diagram of the reaction. And then we can see here the first energy, that is the activation energy which is needed for the first maxima is higher as compared to the second maxima. Now you can see here how the reaction proceed in case of SN1 reaction. So look at here. So this is a tertiary butyl bromide. It goes up to this first maxima where the bond breaking takes place, that is the carbon halogen bond. Then carbocation formation takes place. In the second maxima, nucleophile approaches and then it collapses into the product and it gives the tertiary butanol as you start with the tertiary butyl bromide. So this is the energy profile diagram. Here the bond breaking starts, carbon halogen bond breaking start at this maxima. Therefore, bond breaking processes requires more energy. Therefore, the energy of activation is more for this. After the breaking of bond, then there is a formation of carbocation, the little bit energy get decreased. And then in the second step, the nucleophile approaches to the carbocation. So here again, there is a increase in the energy. So that is the second transition state we call. And here the nucleophile approaches to the carbocation and then it will collapse into the product. So this is the energy profile diagram regarding the SN1 reaction. Now the next important point is stability of carbocation. So for the stability of carbocation, as the carbocation is electron deficient, a positive charge is there. So that indicate for the stability of this carbocation, what type of groups we need? We need electron donating groups. So electron donating groups stabilize the carbocation by dispersal of positive charge. Due to that, we call it is a delocalization of positive charge. So for the stability of the carbocation, we always need electron donating group. So if the electron donating groups are present, then it accelerates the rate of SN1 reaction, and exactly opposite, if the electron withdrawing groups are present, which is attached to the carbocation, the role of electron withdrawing group is to withdraw the electron density towards itself. So this carbocation is still more and more electron deficient. So we call this is a localization of the charge. Because of that, the rate of the SN1 reaction get decreased. Now, the stability of carbocation depends on these factors. The first factor, inductive effect, second is resonance effect, and third one is the hyperconjugation effect. Now, in inductive effect, all alkyl groups are showing electron donating inductive effect, while these all groups, chloro, bromo, fluoro, iodo, hydroxy, nitro, and amino, all these groups are showing electron withdrawing inductive effect. So you can see here that all these methyl groups are showing electron donating inductive effect. Therefore, this is a tertiary carbocation and which is more stable carbocation. But these two carbocations are unstable due to presence of electron withdrawing groups, and that group show minus I effect. Now the second factor is resonance effect. So in resonance effect, the delocalization of pi or non-bonding electrons. Again, the resonance are of two types, electron donating resonance effect and electron withdrawing resonance effect, that is minus R. So if the chloro, bromo, fluoro, iodo, hydroxy, amino, alkoxy, if these groups are attached to the conjugated system, then this group shows electron donating resonance effect. But if nitro aldehyde functional group, carboxylic functional group, and ester functional group, if these groups are attached to the conjugated system, then this group shows electron withdrawing resonance effect. So let us talk about the first type of carbocation is a allylic carbocation. So what is allylic carbocation? These two carbon are of sp2 hybridized carbon, and next to that, this carbon we call it is a allyl carbon. And allyl carbon, there is a positive charge on this allyl carbon, so we call it is a allylic carbocation. Now you can see here resonance. So that though it is a primary carbocation, but still this carbocation is more stable because of the resonance effect. The neighboring pi bond involved in resonance, and you can see the charge is initially present on this carbon. After resonance, the charge is on this carbon. So we call this is a charge is delocalized from one atom to another atom. If the charge is delocalized, then that structure is always more stable structure. So allylic carbocation in this case, though it is a primary carbocation, but it is still more stable due to electron donating resonance effect. The another type of a carbocation is the benzylic carbocation. Now, benzylic carbocation, this carbon which is attached to the aromatic ring having a positive charge, so we call this carbocation is a benzylic carbocation. Now, as this is attached to the conjugated system, no doubt it is a primary carbocation. So on the basis of the stability of carbocation, that is tertiary carbocations are more stable as compared to secondary, as compared to primary. But though it is a primary carbocation, but it is attached to the conjugated system. So because of that, there is a electron donating resonance effect. So these resonating structures we have shown over here, and you can see the positive charge from this carbon, it goes to this carbon. In the next structure, it goes here. And in the last structure, it goes here. So one positive charge can be shared by 4 carbon atoms. So that structure is highly stable. So if the charge is delocalized, then the structure is highly stable. So though it is a primary carbocation, but this is highly stable carbocation due to electron donating resonance effect. Same here, that amino group having unchaired pair of electrons. So again, this is an electron donating group. It transfer its electron density to this carbocation, though it is a primary carbocation. You can see in the resonating structure, the positive charge instead of on this carbon, now it is on the nitrogen atom. So positive charge is delocalized from one atom to another atom. So again, this carbocation is highly stable though it is a primary carbocation. But exactly opposite here, now nitro group is electron withdrawing group. So electron withdrawing group shows minus R effect. So whatever the resonance effect is shown here, that is a electron withdrawing resonance effect. Because of that, this aromatic carbon experiences a positive charge. Hence, these two positive charges are close to each other, that is the which is highly unstable situation. And at the same time, now as this ring is no more electron rich and it withdraw the electron density towards itself, that means the positive charge, instead of delocalization, the concentration of positive charge increases. That means the charge, positive charge, is localized charge. So this carbocation is highly unstable. So minus R effect decreases the stability of carbocation, while plus R effect increases the stability of carbocation. Now this is the third factor, hyperconjugation effect. So what is hyperconjugation effect? It is the delocalization of sigma bonding electrons over pi bond. So look at here, this is a tertiary carbocation and this one is the alpha carbon. So if you know that is a living group is attached to this carbon, so we call this as a alpha carbon. So all the remaining carbons are beta carbons. So these are the beta carbons. So for the hyperconjugation effect, we need a beta hydrogens. So number of accordingly the now here there are 9 number of beta hydrogen. So the number of beta hydrogens increases automatically. The hyperconjugation effect also increases. By you can see here now this proton, that is which is that this is the beta hydrogen. This beta hydrogen takes part in the stabilization of carbocation. There is a positive charge on this carbon, so this is the empty orbital, so there is a positive charge. So this positive charge, this hydrogen get, you can see here in this structure, this hydrogen remove as H plus ion. If it remove as H plus ion, then it forms a double bond here and it gives you a double bond and this is H plus. So now as the charge which is initially present on this carbon, now this charge is on the hydrogen atom. So again, you can see one more hyperconjugation structure. Again, there is a beta hydrogen here. So you can see every time the sigma bond is going to break, that is carbon hydrogen sigma bond is going to break. And because of that, it neutralizes the positive charge on carbon. But this effect is less effective because there is a sigma bond breaking, and whenever as you know, sigma bond breaking requires more energy. Therefore, as compared to inductive effect, resonance effect, this effect is less powerful for the stabilization of carbocation. That's why we generally talk about the only inductive effect and resonance effect when we have to check whether the carbocation is stable or not. Now the next point is the stereochemistry of SN1 reaction. So when we talk about the stereochemistry, so for that, the starting compound has to be optically active. There has to be a chirality center in the reactant, and theoretically, the nucleophile can approach the substrate from the both side of the intermediate carbonium ion to give 100% racemization. So as we already seen in the previous video, that carbocation is a planar and therefore there is equal chance for attack of nucleophile from the front side as well as from the back side. So we get 50% inversion at configuration and 50% retention of configuration. So together, theoretically, the expectation is what? It has to give 100% racemization. But the if the carbonium ion is stable, the nucleophile can attack from both the side, and the expected is what there has to be 100% inversion. The expected is there has to be 100% racemization. But sometimes we never get that type of 100% racemization. Instead of that, there is more percentage of inversion product. So when we get the more percentage of inversion product, so that type of mechanism is called as ion pair mechanism in SN1 reaction. So let us discuss about the what is the stereochemistry of the reaction. So this is the same that I have shown over here, that nucleophile can approach from this side, it can approach from this side, so that it gives 50% inversion product and 50% retention of configuration. So together it gives a racemic product, and racemic product is optically inactive. So for the SN1 reaction, theoretically what we expect, so expected is racemization, but here look at, as we start with the 1-phenylethyl bromide, that is R enantiomer, the first step is the departure of leaving group forming a carbocation. So it gives a carbocation. So water molecule in the next step attack either from this side or it attack from this side. So backside attack or front side attack. So with respect to that, it gives the final. If it attack from the front side, then it gives 50% R enantiomer, that is R1 phenylethanol. If it attack from the backside, then it gives 50% S enantiomer, that is S1 phenylethanol. So together 50% S and 50% R, together it is 100% racemic product. So racemic product is optically inactive. So expected in SN1 reaction is, the if we start with optically active compound, you end up with the optically inactive product. So this is the expectation from the SN1 reaction. But instead of expecting things, now you can see what is the next point, that is the ion pair mechanism in SN1 reaction. So what is the meaning of ion pair mechanism? You can see here in the first step, now this is R2 bromo octane. In the first step, there is a departure of leaving group, but this bromide ion, it is still in the contact with the carbocation. So it is not far away from the carbocation. Therefore, we call this is a ion pair. If they are not getting separated very well, still the Br is close to the carbocation. So you can see here, if that is the situation, if there is a formation of ion pair, then the attack from this side, that is the attack from front side, is a little bit hindered. The reason behind is, this is Br depart with electron density a minus sign over here, while the incoming group also having a electron rich center, the negative sign, there is a repulsion. So nucleophile cannot attack from the same side of the leaving group. So the front side is a little bit hindered for the attack of nucleophile. But that is not true in the case of a backside attack. So backside attack is possible here. So the nucleophile approaching, more and more percentage of nucleophile approaches from the backside of the leaving group. So because of that, you get the S2 octanol with the more percentage, while R2 octanol with the less percentage. You can see here, we get 83% S enantiomer, while 17% R enantiomer. So what this indicate? This indicate that instead of getting 100% racemic product, we get more percentage of S product. And S product is what? As we start with R, you can end up with the more percentage of S product, means what we have to say, there is an inversion at configuration, and that inversion is because of what? That inversion is because of ion pair mechanism. So overall, so what I had to say now, this is 17 molecules of R, whatever the optical activity caused by 17 molecules of R, that optical activity getting cancelled by the 17 molecules of A's. So you subtract the 17 from this A's, so it gives what? 66. So 66% S enantiomer, only 66 molecules are responsible to show the optical activity, while 17% R, and the 17% S from this, that is total 34% racemic mixture we are getting. So 66 molecules are responsible to show the optical activity, and that optical activity is, of course, if you start with R, you end up with S, means overall in this reaction there is inversion of configuration. So the theoretically expected stereochemistry of the product in case of SN1 reaction is 100% racemization, but practically, due to formation of ion pair, the exact opposite situation we can see a little percentage of racemic mixture while the more percentage of the inversion of configuration. Now the last point in this is effect of solvent in SN1 reaction. Now, when we talk about the SN1 reaction, that is Rx is a polar compound because of presence of X, that is the heteroatom. So the Rx is a polar compound. Nucleophile is also a polar. So we need, for SN1 reaction, to get the homogeneous medium, we need a polar solvent. So polar solvent increases the rate of SN1 reaction. Now in polar solvent, as you go on increasing the polarity of the solvent, automatically it increases the stability of the carbocation. So look at here, look at this table, the ethanol and water. The water is more polar as compared to ethanol. The reason behind is here only one proton which is attached, one hydrogen is attached to the highly electronegative oxygen atom, but in case of water, the two hydrogens are attached to the highly electronegative atom. So there is a more electronegativity, if there is a electronegativity difference is there, then that bond we call it is a polarized bond. So water is highly polarized as compared to ethanol. So look at from 100% ethanol, if I change it to 80%, 40%, 50%, and 100%, that means we are going to increase the polarity of the solvent. So 20% water, then you add the 40%, 50%, and 100%. That indicate from ethanol to water, we are going to increase the polarity of the solvent, and you can see here the rate of SN1 reaction also increases in the same direction. So for the SN1 reaction, we need a polar solvent. So if we increase the polarity of the solvent, then automatically the rate of SN1 reaction increases. So you go through this book and you refer this video for the more understanding.